Is a project that was conducted here. Actually, it makes it a little sad to talk about it. Maybe I should talk about it. So I get really tied to the people I work with. So if something happens to them, I sometimes stop working completely on whatever it was I worked on with them, because working on it reminds me of them. So there's a phenomenal programmer here named Carl Bredlaw, and unfortunately he has lung cancer, and they just stopped his treatment. But if you look online at his webpage from Montclair, you'll see that he's coded NIM, so you can actually play NIM, and you can see that win-loss sequence. I think he's done NIM. And he's also programmed in NIMBR sequences. I told you a little bit about NIMBR sequences. So back when Michael Jones and I were doing the NIM as a dynamical system, he was looking at NIMBR sequences. And a student here at Montclair was working with him on the project. And that student now has her PhD, and she's at Albion College. They wrote a paper, and the paper was submitted somewhere, and it didn't get accepted because one of the guys that wrote your book reviewed the thing and said, well, you didn't look at this and you didn't look at that. So they just last year, I think, resubmitted it, if I understand the story right. And the person who reviewed it said, I think what you did is great, but this doesn't look like what I know as the definition of NIMBR sequences. So Mike said he got it back, and he looked at it and he said, right, we didn't have the definition quite correct. So that paper is fully fleshed out, and he said that if you take that paper, you would have to recast it in the correct definition of NIMBR sequence, which I gave you the definition that he gave me, so I'm not quite sure it's right anymore, where it's the number, the element in the NIMBR set, that number in the NIM subtraction set, which gave you the win. It's not just, like sometimes you can use two of the elements to get the win. So it actually is a sequence of integers that belong to that subtraction set. So you can take a look at that paper and start to finish that out. He said you could reprove everything that's in their paper for just win-loss sequences that we've been doing in class. So there's many offshoots of this, of just that work alone that you could take as your final project. So, and the same goes for dots and boxes. I find out more and more every day what's open, and so you can take out little pieces of it. And domineering, and we haven't even talked much about cram. So there's different games that you could just, I would say, select the game that you like, and I can give you a defined problem to start playing around with. We talked about the whole idea also of the playing around with. You know, I told you I've done this before in a class, a Common and Torts class. At the end of the semester, I was like, oh, I can't even bear the thought of giving a final exam in this class, because it's a lot of similar to what we do in here. And I asked the class to just fool around with some problems, and 30% of the class were like, woohoo, we've been waiting all our lives to just stop looking in these content boxes and memorizing it and spitting something out. So they were delighted. But the other 70% felt uncomfortable because they wanted me to tell them what to do. And I would tell them to just fool around with them. Obviously, I was in that 30% that felt very comfortable with the idea of fooling around with something and just playing around and seeing what I can find. And so I would imagine that something similar may happen here. So the earlier you start, the better, because there might be a discomfort level of just getting started. I have a feeling you're just going to like messing around with it. Some people like that a lot, and some people have to get used to it. But once you get used to it, then you've done it before. It's something like riding a bike. You've done something, just exploring by yourself, and it makes you more brave. I think mathematicians in general, they might think of themselves as being smarter than the rest of the population, but truly they're more brave because they'll take on anything and say, I don't care how hard that looks, I'm going to start working on it and playing around with it. And it also takes patience. Patience and bravery. That's what makes a mathematician. And a little uncleanliness. Okay, we were yesterday, or third Tuesday, at a point where we were coming up with this recursion and had written it this way. And I had you mess with the recursion with a subtraction set of size 3, and you wrote down the formula for the initial condition. And so everything is kind of, I should have you at least believing that this is the recursion formula that you can now write down to generate that win-loss sequence. And I even suggested for you a way to win, for sure. Just take a subtraction set with 2 elements in it, and then make sure that A plus B is prime, right? And then you know that the win-loss sequence pattern has to repeat at A plus B, right? You know that the cycle is. Okay, So I want to recast this a little bit, and I don't have it in the PowerPoint, but I want to show you something that you probably have seen elsewhere. I mentioned a little bit about differential equations because that is the viewpoint that I'm looking at to write down this formula and start thinking of it this way. But in differential equations, I'm not sure in the class itself whether you talked about differential equations which had more than one derivative in it. So for example, you could have a differential equation which has a second derivative in it. And we call this a second order differential equation because it has a second derivative in it. But it's not just called a second order differential equation because of that. It's also called a second order differential equation because I need to feed it an initial condition from R2. And that might not seem obvious initially, but I'm going to show you a sneaky little way to do this. So what we do is we do a change of variables. It's always that, right? In every math class, starting with Calc 2, it's always a change of variables. So you take u equals y and v equals y prime. And when I take u prime, I get y prime, which is really our v. And if I take v prime, I get y double prime, which is, from the formula, y, which is equal to u. So I can recast this whole system as u prime equals v prime is equal to u. And in fact, if you took this as a class from certain professors, they probably transformed this into a matrix equation, right? So what they did is they said let x bar be a vector, uv, like that, and they did x bar prime is equal to matrix probably had something like this in a differential equations class, right? So there's a way to express this as a vector. So this is a system of first order equations. For each one of them, they need an initial condition. So your initial conditions look like u at 0 is, you need to give it an initial baseline for each variable. Or if you think of it as a vector, you have two components. So you're living in R2. So really, I'm taking vectors in R2, and I'm looking at a trajectory that follows this vector in R2. Kind of make sense? If you haven't taken differential equations, it should kind of make sense a little bit what I'm doing, because everybody in here has linear algebra. I can do the same thing to that this nim piece over here. And I'm going to show it to you in a paper because I didn't write it out in the slide, but it's actually very, very important. How many of you have seen this before? This changing of a second order system into a system of first order. So some of you have seen this before. If you haven't, it's really cool. Nimrod, that's right. So you could do the same thing. I'm going to see if I can blow this up a little bit more. To a recursion equation. So like I did with the u and the v, I can make up dummy variables so that there's a recursion here that's a dummy, and my last one is the one where I actually have the recursion, and it's a function of all the previous ones. It's the same kind of idea that I did here. So I just a change of variables, and I don't know if I have above what that change is. Yeah, math papers are very terse, so I don't think I have above exactly what that change of variables is. And I'm not going to go through it in here. It's not that entertaining, really. But you just come up with a system of equations And your initial condition, just like I wrote it in vector form here, so here it would be that x at 0 is really u at 0, v at 0. All the initial conditions would line up in vector form. So what you're doing here is you're really taking a vector. How many initial conditions will you have in this? If I did a recursion like this, each one of them is first order. So this one would need a seed of y2 at 0, for example. And this one, we y1 at 0. And here we need y2 at 0. And we need one for each one. So how long is our vector going to be? What's the size of our vector that I'm going to have to feed it to start this recursion going? How many components do I need to fill in? Like here I needed 2, because I have a system of 2 equations. Here I have a system of how many? 4. SK, right? I have a SK. I have 1, 2, 3, all the way up to SK, right? I kept saying order SK last time. That's why, because I can recast this all as, instead of being in the original form, of the recursion, I can't start this going until I at least, for example, if my largest element in the set was 7, I can't get this thing going until I'm at the 7th position, right? Once I'm at the 7th position, it starts going. So I have to feed it information at least 7 positions, right? This is just a different way of saying the same thing. If I write it this way, to run this recursion, I need at least 7 points to start, right? The size of that vector is going to have 7 components to start, or in this case, SK, because I've left it arbitrary. So I could write it like I did this thing over here. I could write it as a vector, y of n plus 1 is equal to a map, like the button on your calculator that you're pushing over and over. I called it d, which is a pretty bad way to call it, based on y of n. So what I'm doing is I'm iterating an n-dimensional or an sk-dimensional vector over and over and over again. And this is dependent on the subtraction set. And the initial condition is going to live in z2 of sk, because the initial feed I have to give it has sk elements. And just in case you forgot, I've been calling the subtraction set arbitrary like this. If you don't want to see all those letters, you can think of, for example, what did we do last time? S is equal to 4, 2, 4, and 5, right? So what would the size of your vector be for here? What's sk? No, it would be sk would be 5, right? So the feed you have to give it to get the recursion going is at least 5. Make sense? So your initial condition is going to live in a vector with at least 5 components. And that's really important, because what that tells me is that if I was living in this world, for example, I can write you down. It's not going to be fun, but I could write you down all combinations of zeros and ones of length 5 on the board here today. It would make for a very boring lecture, because we'd have 2 to the 5th things to write down, right? But I can write them down easy. And I can make you write them down, but I'm going to do that. You write them down, you can literally put them down and say, okay, I'm really pushing a button over and over on these elements, and there's only 32 of them. So eventually it has to cycle, because it has nowhere to go. So that proves that there's going to be a cycle. And this is posted on Canvas. See, I wrote it this way. And it proves a lot more than that. We have an example in here, which I meant to show you as a picture. I'm going to show it to you one more time after I get into it a little bit more. I took a subtraction set. Oh, not 200. If I took the subtraction set 2, 4, I can apply that map to all the possibilities. I can just rearrange all the possibilities. And what you find out is that there's these initial seeds that drop down into cycles. They must drop down into cycles. So let's say this was the first thing I saw in my calculator, and I'm going to push that DS button. If I push it once, it ends up at this number, at this vector. If I push it twice, it ends up at this vector, and then it goes through the cycle. If I start out with this seed, this set of initial conditions, it's not the NIM initial condition. The NIM initial condition is very specific, right? You guys can actually, if I asked you the NIM, you would actually put down the right zeros and ones. It turns out the NIM initial condition looks, I think this one is it. It drops down to a cycle right away. But so this one drops down here, and then it goes into this cycle. This turns out to be the NIM cycle. So it's the period that you would get if you were playing NIM. There's some other cycles that have nothing to do with NIM. So here's a sub-cycle that I could start out with. This is not an initial recursion that you would start out with that's anything to do with NIM, and it drops down to something else. If you start out with this one, you drop down to the NIM cycle. So it looks like most of them are dropping down to the NIM cycle. But what Mike and I found was this one, all zeros, drops down to the NIM cycle. And that's all we need to know. Because if the zeros all drop down to the NIM cycle, I don't have to figure out what the initial condition is for NIM. It's pretty huge, because now you can run a computer to do things for you. So bizarrely enough, I worked in an area called cellular automata. It has to do with neural networks, machine learning, that kind of stuff. And in that area, they talk about something called Garden of Eden points. Garden of Eden points are exactly what's depicted in this picture up here. They're vectors that you can start and flow down into, but that you never cross them along a path. They're like seed starters. So they're the beginning. That's where you start. So there's 4 Garden of Eden points here, or vectors. So another way to say this is if I'm looking at S equals 2, 4, and then my space I'm living in is Z2 to the 4. Well, there's certain vectors in Z2 to the 4 I'm never going to see on a path down while I'm iterating this map. Those are called Garden of Eden points. So for example, I just wrote out 2, 4, what it would look like if I played NIM. 1, 1, 1 is a string I will see, so that's not a Garden of Eden point because it's there in the cycle. 0, 0, 1, 1 is a string I will see. There it is. I can find it in my cycle. So I'd like you to do that. List out all the 4 elements of 0, 1 and tell me which ones you will see in this cycle and which ones you won't see in this cycle. Yeah, use 2, 4. 2, 4 is not too bad. Well, it's only the 4 you care about when you need to list everything, right? So the way to do this systematically, if you haven't done this before, is you did it in probability. Everybody had to take probability, right? So you start out with 0, and the next element, so you're trying to fill in what the components can be. So the next element could be a 1 or a 0. The next third element could be a 1 or a 0. The fourth element could be a 1 or a 0. And the fifth element could be a 1, or here, 1, 2, 3, 4, got it. Then you trace the paths. 0, 1, 1, 1. Just trace that path. 0, 1, 1, 0. And then you keep going. How you could have started out with a 1 first, right? It would be all the same trees, right? So you just replace all of these with a 1 first. They're called binary trees. Done this in probability? All right. So list out all your 4s. How many should you get total when you do that? It's multiplication rule for probability.